Hello, this is Dr. Brothers, and today we're going to go through the basic procedures for troubleshooting electronic circuits. The motivation of this is that in the junior design class, we have just ordered our PCBs, and the majority of you are in the lab right now, breadboarding, getting motors to run. So we're going to go through this slide deck. This is the basic procedure for troubleshooting. This was put together by Kevin and James in the ECE department, and then I have modified it just a little, added a little bit more detail. So let's get going. First thing we're going to do, here's the general outline. Discrete components. These are an electronic device that is composed of a single element. Examples of these: resistors, capacitors, diodes, transistors, inductors, fuses, and integrated circuits. So an integrated circuit is a device that's composed of many millions of capacitors, resistors, and or transistors. They're sometimes called a chip or a microchip, but they're still, when we look at a PCB, when we look at a physical circuit that we have created, it's one part. So these discrete components are each the individual parts that we're going to put down on a PCB in order to make it a circuit card assembly. So with all of this, the data sheet is the most important tool that you have. The data sheet is a document that summarizes the performance, technical characteristics, demonstrates the schematics that you use for that component. So when you are doing debugging, you have to have data sheets. So we're going to talk about these items in this lab or in this PowerPoint. And then in this actual PowerPoint, there are procedures for testing each one of these. I'm not going to go over the procedures during this lecture. What I want you to do, we're going to have a homework assignment, and in that homework assignment, you're going to go and check out a PCB from the Senior Design Lab, and you're going to go through and you're going to actually test each one of these. So you'll use this PowerPoint presentation as a reference in order to go and get those parts, check them out, and do the troubleshooting. All right, so what we're going to do, we're going to go through each one of these discrete components real fast, talk about them, tell you what they are, and then we'll go into a little bit more of how they're tested and how you look at them. So symbols and diagrams of discrete components. First off, we're going to look at resistors. So on this page, these are all resistors. The first resistor is the standard resistor. The majority of you are probably very familiar with this. On the left-hand side, we have a surface mount resistor. And what you do, this goes on top of the PCB. There would be two landing pads. You put this on the pads and you solder on each side of it to make the electrical connection. This is a through-hole resistor with stripes on it to give color coding. You would put these leads through holes in your PCB and then solder fill those holes. Variable resistor. This is also called a potentiometer. Now, a variable resistor has this very sturdy looking handle on it. This is made for user input. It's made for a user to take this handle, turn it up, turn it down, turn it up, turn it down, and it is designed and built for that repetitive input motion. This is opposed to the adjustable resistor. This does not have a handle. This has a small screw terminal where you can adjust it. This device is made to maybe calibrate a circuit. So maybe you adjust this once in a lifetime or once a year, or once a month, whatever the scenario may be. The adjustable resistor is very delicate and can break easily. You do not want to use one of these as a user input device. The symbols for all of these are on the side here, where a variable actually has this arrow through it. An adjustable, you can see it looks like it's tapping off at a certain point in the resistor because it can move back and forth, but it's supposed to be set and you're supposed to pretty much forget about it. This is a photoresistor. Many people have probably heard of a photodiode. Photoresistor, its resistance changes based on the degree of illumination. This is a tapped resistor, and this one is a power resistor, and a lot of the tapped ones are power resistors. So there's this collar that can be moved back and forth along this, and then once it's set, it's tightened down, and that determines the resistance. So it's adjustable, but again, you're not meant to change it. You're meant to set it, and that's it. So, and then thermistor. This is a device where the resistance will change based on the temperature. And there are a whole bunch of different styles and looks of these. A lot of them look like a capacitor, but they're not. They're a thermistor. So you need to look at the number that's on the device to know what it actually is. Speaking of capacitors, here we go. We have the normal capacitors. Here are two symbols for the normal capacitor. Here is an electrolytic symbol, and here is a variable symbol. The normal capacitors, the surface mount one looks just like the resistor. So you really need to have the data sheet. You need to look at the numbers that are printed on top of these and understand what they are. These are just normal through-hole capacitors, a couple of different styles. Electrolytic. These are polarized and must operate at a higher voltage. You need to be really careful about these, especially as you get to the bigger electrolytic capacitors. If you are playing, say, with a computer power supply, if you're playing with an old school TV, they have a lot of these big electrolytic capacitors that can really hurt you if they're not discharged before you operate or before you do service on these. So if you see an electrolytic capacitor, be careful with it, and it is a good idea with the bigger ones. Make sure to discharge them before you start to play with them. And to discharge cap, that means that you're going to connect it to something that can take the voltage out of it. We also have a variable. This can change slightly. You can see that it's kind of circular, and it has a screw terminal on the end of it. It has two plates, and that screw terminal will move the plates closer together or farther apart to create a different capacitance. Diodes. So we have a whole bunch of different styles of diodes. First, the symbol at the top, this is our normal diode. You put a forward bias on the voltage and current will flow through. You put a reverse bias on the diode, nothing happens. Now, you have a Zener diode. That one's a little bit different. It has to overcome a forward bias, so there is some point of forward bias, and once you overcome that forward bias, it allows current to flow. But there's also a reverse bias. So if you turn it around and put a large enough reverse bias on it, current will start to flow back the other way. Schottky is kind of the same thing, except again, it only has a forward bias on it. And so this one, a lot of times, this is very useful for getting rid of a low noise signal. Say you want to connect a push button, and you want to make sure that that push button is pressed in a solid manner before allowing the current to flow through. This will take off a lot of the debounce on it and make sure that there's a solid connection before it shoots that current through. So I've used these to make a one-shot circuit before, where it only goes off when it has that nice, strong, solid connection. Varactor, I think I'm saying that right. This circuit describes what it is, so it has a capacitor in line with the diode, and so it will work with these two in parallel. A tunnel diode, this one has a region where it's going to open up, and then as it approaches V2, it chokes off the current, and then once you get enough forward bias on it, it again overcomes that and releases the current and lets it flow through. So really in these you want to operate between regions 0 and V2, and so this can help control your system and make sure you don't get too much current going into certain devices if you're leading to an overpower situation, if you're pulling too much power. Light emitting diodes, LEDs, everybody knows what those are. They're just the little LED lights. Then we also have a photodiode. This is a lot like the photoresistor, except we are going to allow the voltage to flow through as the light is impacting on the sensor. That brings us up to transistors. Now, I'm a digital guy, so I'm going to talk about transistors from the way that I use them, and I use them as switches. But they can also be used for amplifiers, variable resistors. So amplifiers are the simplest way to use them. Switches are the simplest way to use them. And oftentimes for me personally, if I want to do something as an amplifier, I'll use an op amp just because they're much easier to control. But we have three different types of transistors that we have access to. We have BJTs. That's the first style here. These are controlled by both the base current and the terminal voltages. So these can be used for switches, amplifiers, a whole bunch of things. You have very fine degree of control on them. For a digital guy, you know, they're a little bit of a complex switch, but they are very nice. You have a JFET, voltage controlled, doesn't need the bias current, so it's purely dependent on the voltage. These are the simplest to use. They can be used for switches, amplifiers, variable resistors. You also have MOSFETs. Those are on the very right-hand side. Voltage control does not need a bias current. Again, these are more robust, but they are also less sensitive. So if you need something like a differential circuit where you have two transistors, you want to use a BJT or a MOSFET, a BJT or a JFET, because the MOSFET is harder to balance against each other. It's harder to control, but it's more robust, so it can work for big voltages, big currents. So that's kind of how I look at these three components. Obviously, if you have an analog person, they can give you a lot more detail on how to use these and the proper use of them. From my viewpoint, these are great switches. Moving on, inductors, fuses, integrated circuits. For inductors, for the most part, again, being that I'm a digital guy, I usually look into the data sheet to see the recommended circuit configuration for a given device, and 90% of the time it just requires an air core inductor in those circuits. So very rarely have, if ever, I don't think I've ever used anything exotic in an inductor, but they're out there. Fuses, we have another lecture in which we talked about fuses, but there are some of the different symbols that you can put onto your circuit. Integrated circuits, like I said, integrated circuits, these are extremely complicated devices. They can have millions of resistors, inductors, transistors inside them, capacitors inside them. And here are some example circuits that you can see. So here's a schematic where it has a bunch of FETs inside it. Here is a circuit where it's a quad pack op amp. And here's a circuit where it's a 7-segment decoder with a bunch of digital logic inside it. In order to test and debug an integrated circuit, you really need to understand what the digital circuit does. And oftentimes the way you will debug this is to turn it on and to start to stimulate it and see what the output is and see if it matches the data sheet. So it is critical to have the data sheet for these components when you're going through and doing a debug on the circuit to make sure they're operating correctly. So here are the basic tools that you're going to use for doing debugging. You need a digital multimeter. This is the universal tool that we're going to use for almost all of our debugging. You can use more complex devices. You can use oscilloscopes. You can use spectrum analyzers. There's a lot of other equipment, but this lab is focused on using the digital multimeter, and you can troubleshoot pretty much anything with one of these. You're going to need pliers and cutters for stripping wires, putting components in, screwdrivers for putting in the standoffs, screwing in wires into terminal blocks, safety glasses, magnifier. These circuits are very small, so use the magnifying glasses. Use the safety glasses. If you are debugging something and you accidentally short it out and it's a hot circuit, it can blow up, and you want to protect your eyes. Wire brush set for cleaning off old solder, and if you have to cut a trace, you can use that to clean the area. X-Acto knife, this is what you use to cut a trace. So maybe your PCB is wrong and you realize that you ran a trace to the wrong point. You will have to take an X-Acto knife and physically scrape off the trace from the PCB. And then you might need to solder a wire onto that trace and take it to the correct location. Flashlight or other illumination, a lot of the times when you have the magnifying glasses, it has a light in it. tweezer sets, you do not want to have your fingers down there as you're trying to solder. So having a set of helping hands or having a tweezer. Helping hands is not your friend's hands. It's actually the little mechanical hands. Isopropyl alcohol for cleaning off the circuit, and then schematics, data sheets, all the documentation. You need to have it at your fingertips available so that you're not trying to go out to the internet and find it when you're actually doing the troubleshooting, when you have that valuable time when you're in the lab with your team. Make sure you have everything organized. Make sure you have your parts. Make sure you have your equipment so you can just get to work. Here's the digital multimeter, and for those of you who have not seen it, this thing is great. It has a bunch of functions. It can do voltage in both AC and DC. It can do millivolts, both AC and DC. It can test ohms. It has this continuity beeper, which what that does, when you, for instance, connect leads together and close the circuit, it will beep. That goes hand in hand with the diode test. And then there is a selection for measuring the capacitance. And then you can measure current, both AC and DC. We're going to talk about measuring current specifically later on in this presentation because it is very critical that you understand how to measure current before you try to measure the current. Here's the data sheets. We've talked about them before. They're wonderful. You need to have your data sheets. Here's our friend, the 555 timer. And then this is a voltage regulator. And here's some more characteristics about the 555. So get your data sheets for all your parts. Have them in a folder that's easily accessible from your device or have them physically printed out with you. Electrostatic discharge. There are whole classes that you can take on ESD. As you get to higher frequency ranges, ESD is more important, but as we're operating on these low frequency range devices, it is still important, especially right now while we're doing a lot of the remote learning. We are trying to operate during COVID, so a lot of people might be working from their home. If you're working from your home and you are working in a space that has carpet on the floor, that's a bad idea. Carpet generates tons of static. If you are working somewhere where it's carpet on the floor and then your desk does not have a ground mat, you are really not doing yourself any favors, and you could easily short out your electronics by ESD. Here's the anti-static mat that I'm talking about. You want to have one of these. It has these little plugs on the end of it. These plugs are what you connect to a ground source. So if you get one of these mats, you lay it out on your table at home, and you say, now I'm protected from ESD. No, you're not. Not only do you connect this to put it out on your table, you must connect it to the house ground system. So a lot of times what you'll have to do is find an electrical outlet and take the screw off in the middle of the outlet, and that's what you'll put the wire lead to ground it out. And then you want to connect yourself to the mat, so they have wrist straps that connect to the mat. A lot of times with the electronic equipment that we're using, as long as you have the mat and as long as you touch that ground terminal before you start messing with it, you should be pretty good. That discharges the static. Here is an anti-static bag. Inside that anti-static bag, you would want to put your electronic devices to transport them. However, I've noticed people that have used this anti-static bag for the mat. Do not do that. The anti-static bag actually will transmit the voltage. So do not use that as your mat. The anti-static bag is what you use to put electronic components in. The anti-static mat is what you put on the table. Don't mix those together. So, checking with your digital multimeter. Before you start working with your digital multimeter, one of the things that you want to do is make sure that it is operating correctly. So take your digital multimeter, take the leads of it, and tap them together with it on the continuity check setting. That should beep and you should look at the display and you should see that it's very near 0 ohms. As long as that happens, your digital multimeter is calibrated for at least the resistance measurement. So, how to approach troubleshooting electronic circuits. This is where I'm going to start clicking through the slides, and you are going to come back and read these as you actually go through and do the troubleshooting of your individual circuits. So come and read these detailed and make sure you understand these approaches. But one of the things that you want to do, I'll go over this a little bit. One of the things that you want to do when you first get your PCB, you first want to do, you want to take it and populate it. So you'll solder on all your components. Once you've soldered on all your components, then you want to take your digital multimeter and you want to check your PCB before you ever apply power. So check your voltage rails, make sure they're not shorted to ground. Check the different leads of your ICs and make sure that when you soldered your ICs on, you didn't create a solder bridge between them. So you can just go through and do a continuity check and make sure that your ground is not connected to 5 volts. Make sure your 5 volts is not connected to 12 volts. You know, do all those types of checks and just make sure that you have double checked your voltage and your ground planes at least before you turn on power. When you turn on power, connect it, turn on power, let it run for just a couple of moments and then turn it off. You want to then inspect your circuit and make sure that you didn't burn out any traces and that none of the pieces are getting hot because they will physically burn out. That's what's shown here. So here is an example of a bad solder. And so this you would want to catch before you ever applied voltage. But as it gets hot, you can see how this actually burnt the components off. So it will get really hot before this happens. So if you apply power for just a couple of moments and then turn it off, you have a possibility of checking this before it burns out. But most of the times electricity is so fast that it'll get up to temp real quick if you have a short in your circuit, and you'll hear it just pop and you'll smell the smoke. So this is one of the reasons you want to double check before you ever apply power. This is another one where you can see the burnt area up at top. So before you apply power, use your schematic to check and see the values and the connections of the circuit that you are checking. Test it with your digital multimeter to make sure they are correct. If the schematic is not available, you can still check the components on the individual board as follows. This is where I'm going to click through it. Here's how you check a battery. When you check a battery, make sure you're safe. If you short out the battery, it can spark. So be sure that your multimeter is set to measure current. Be sure you are not, let me repeat again, not set to measure current, as this would short out the battery. So make sure that when you are going to check your battery, you are set to measure voltage. Because otherwise, if you're set to measure current, it would short the battery. It could burn out your battery, your power supply system, whatever you're checking, and also possibly the digital multimeter. Checking fuses, here's the procedure. Troubleshooting, checking resistors. Here's the color bands for the resistors. Here's how you check resistance. Checking diodes. Here's how you check diodes. You can also check LEDs in the same manner. This is using the same setting. It's using the resistance, continuity, diode setting on the multimeter. All right, checking capacitors, checking resistors. Here's how you do each one of these. Checking transistors, checking transistors, checking transistors, checking transistors, checking inductors, checking potentiometers, which this is actually an adjustable resistor instead of a variable one. And these are very sensitive, so these break all the time. And here's how you check the voltage regulator. Here's an IC. Checking the IC is very hard because you need to first fully understand the integrated circuit before you can check it. All right, here is how you check the integrated circuit. This is our friend, the 555 circuit, and this is the actual board that you're going to get this week. And the board is going to be provided to you. And some of the components on this board have been we have intentionally made it to where these components are not working. So go through, and your assignment is going to be to pair up in 2s or 3s, no more than a group of 3. And in that, you're going to go through and check each one of these components. So in doing that, you can have one person who's reading the data sheet, reading the procedure, and the other person who's actually working the equipment. If you are a remote student, make sure that you get paired up with someone who is local so that you can work together in order to debug and test these circuits. So, checking current. We're going to talk about this a little bit because it's very important. Never put a meter in current test mode in parallel with the circuit, as this would short out the supply power and potentially damage power meter and the supply. This is the method in which you connect a multimeter to a circuit. You can see that the positive from the battery is actually going through the multimeter. The multimeter is becoming a part of your circuit. It is connected in series to this circuit. And so after the supply goes through the multimeter, then it goes through your device under test and it returns back to the battery. So when you check for current, you have to break the circuit and insert your multimeter in current measurement mode. Make sure that as you do this, you understand that the current requirement, and make sure you understand that you never measure current in a parallel mode. Okay, never just touch it over it like you would to measure resistance. You will also have to power the circuit in order to accomplish this. So this is going to be working on a hot circuit. So use all the proper safety precautions. So also be aware that when you measure a resistance, this is actually going to provide a voltage into the circuit. So you never measure resistance on a powered circuit, because then you would have two voltages that are both going into the circuit at the same time. And you don't want that. So you have to isolate it, or you have to make sure your circuit is powered off. Usually you have to isolate it also to accurately measure resistance. These are the safety procedures. You must read these. Read these before you do the troubleshooting activity. Here is the schematic and the board layout for the troubleshooting board that you're going to check out and go through. Here's the BOM for that board, and this is a schematic symbol guide. Make sure that you have a nice handy reference of all the symbols that we're going to use. So that is everything that I have for troubleshooting a circuit. I hope that you go through and do this. Take your time as you do this procedure and make sure that you read the data sheets on the parts before starting to try to troubleshoot this circuit. All right, have a good day.